Okay, let me ask you this. How sure are you, really, that something, say a chair across the room, has a definite place, even when you're not looking?
Mm.
Or maybe that everyone watching the same event unfold actually agrees on what fundamentally happened, what's real?
Yeah, those are questions we usually just take for granted, aren't they?
Exactly. And that's why today we're doing a deep dive into quantum mechanics, specifically how it challenges our whole concept of reality.
It really does.
Our mission here is to explore some source material that unpacks these, well, pretty unsettling implications. We want to see how quantum mechanics isn't just about weird, tiny particles,
Uh-huh.
but how it fundamentally shakes our ideas about what's real, what's definite, maybe even what we can ever truly know.
It's definitely a journey. It forces you to question things you thought were solid ground. And it's
Abraham.
way more than just abstract physics equations. It bleeds into philosophy, into how we understand existence itself.
Right. So let's start with that first layer of weirdness. Uh, the behavior of particles and this idea of superposition. We hear about wave functions, Schrödinger's equation.
Hmm.
For someone following along, what's the absolute key thing to grasp there?
Okay, so the core idea is quantum mechanics doesn't see a particle as a little point, like a tiny ball. Instead, it's described by something called a wave function.
Okay.
And this wave function comes from solving the Schrödinger's equation. Now, the crucial part, and this is where it gets mind-bending, is that the equation is linear.
Linear. Meaning,
Meaning, basically, if a particle could take path A and it could take path B, because the math is linear, it can also exist in a state that's a combination of both A and B.
at the same time.
A combination, like a superposition. Exactly, superposition. It's not either A or B until something forces a choice, like a measurement. It's A and B together.
So, hold on. This isn't just a mathematical tool we use for calculations.
Yeah.
You're saying the math implies this superposition is physically real.
That's what the framework tells us, yes.
Yes.
Physically real. Even though our normal language just breaks down trying to describe it.
Right. How do you even talk about something being here and there?
You can't, not really with everyday words.
Yeah.
Our intuition is built on, solid objects with definite places. This is different. It shows a big gap between the physics and just, well, human experience.
And this must lead to some really strange behavior for particles, completely unlike anything we see with, say, billiard balls.
Oh, absolutely. Forget billiard balls. Think about this. Put a particle in a box. You'd think it just sits somewhere, right?
Yeah.
But its wave function actually spreads out. It fills the whole box in a probabilistic sense.
The whole box.
Yep. Or consider a particle, maybe a neutrino, from a supernova billions of light years away. Before we detect it, its wave function could literally be smeared across that vast distance.
Billions of light years wide.
Potentially, yes. But then, the instant we measure it, poof, it appears right here at one single point. Like the universe just decided its location at that exact moment. Even electrons in atoms, they're not orbiting like tiny planets. They form these fuzzy clouds, these patterns reflecting their spread out probabilistic nature. Until you measure where the electron is, it's sort of everywhere in that cloud at once.
It's amazing how different the fundamental level is, which I guess brings us to that second layer you mentioned, this idea that things don't even have definite properties until we look.
Exactly. This is where it gets even more counterintuitive, if that's possible.
Yeah.
In our world, an apple tree is either there or it's not, right? Seeing it doesn't make it real.
Right. Seems obvious.
But quantum physics says, hold on. For a particle, properties like its location or its spin might genuinely not be definite until you measure them. Before that, it's not just that we don't know the position, it's that the particle exists in multiple positions simultaneously.
Okay, this is where Schrödinger's cat comes in, isn't it? The famous thought experiment.
That's the one.
A cat, a box, some poison linked to a quantum event.
Yeah.
It ends up being both alive and dead. What's the real point it's trying to make? What does scaling up this quantum weirdness force us to confront?
It's a deliberately provocative illustration. It takes the superposition of a single atom, which might decay and not decay simultaneously, and links it directly to a macroscopic outcome.
The cat's fate.
Right. So if the atom is decayed and not decayed, then the poison is released and not released. And therefore, logically, the cat inside the box is alive and dead, both, before anyone opens the box and looks.
Live and dead.
It just throws this clash between quantum rules and our everyday reality into sharp relief. It forces the question, what counts as an observation? What makes reality snap into one definite state?
So if the math points to this zombie cat state, how do physicists try to get around it? Do they just accept it?
Well, there are attempts to resolve it, but they often introduce their own kind of strangeness. One big idea is decoherence.
Decoherent. Okay, what's that?
The basic idea is that quantum systems are almost never perfectly isolated. They constantly interact with their environment, air molecules bumping into things, photons bouncing off.
Right, the real world is messy.
Exactly. And decoherence theory says these environmental interactions effectively smear out the superposition. They cause the quantum system to become entangled with its surroundings in such a complex way that it looks like it's settled into one definite state.
It looks like it, so it doesn't actually solve the alive-dead problem fundamentally.
Not quite. It explains why we don't see macroscopic superpositions like alive and dead cats walking around. The weirdness gets diluted, spread across trillions of particles in the environment. It explains the appearance of classical reality, but maybe not the fundamental transition from both to either. It shifts the problem in a way.
Okay, so it makes it seem definite, but the underlying quantum bothness might still be there, just hidden in the entanglement.
Kind of, yeah. It's subtle, which leads some people to other interpretations, like the many worlds interpretation.
Ah, many worlds. That always sounds like pure science fiction.
It does feel that way. This idea basically says, okay, the cat isn't alive and dead in this universe. Instead, at the moment the quantum event happens, the entire universe splits into parallel universes. In one universe, the atom decayed, the poison released, the cat is dead. In another separate universe, the atom didn't decay, poison wasn't released, the cat is alive.
So the cat is definitely one or the other.
Yeah.
Just in different realities.
Exactly. The superposition is resolved by reality itself branching, but many physicists find the idea of constantly splitting universes just as bizarre, maybe even more so than a single cat being both alive and dead.
Yeah, trading one weirdness for another, potentially infinite weirdness. It's hard to know which is stranger, which kind of sets us up perfectly for the third layer, the potential collapse of objective reality itself. If universes are splitting, or if observation is key, what does that do to the idea that we all share one single truth?
This is where it gets really profound and frankly quite unsettling. We can explore this using another thought experiment called Wigner's friend.
Wigner's friend. Okay, lay it out for us.
Imagine your friend is inside a perfectly isolated lab. Inside, they measure a quantum particle, say, its spin. They see a definite result spin up, for instance.
Okay, so they know the result.
Right. But you are outside the sealed lab. From your perspective, before you interact with the lab or your friend, the entire system inside your friend, their measuring device, the particle could still be in a superposition.
Wait, so my friend, who is definitely seen spin up, from my viewpoint, they could be in a state of having seen spin up A and D, having seen spin down, until I open the door.
According to a strict application of quantum mechanics to macroscopic systems, potentially yes. Their reality, their definite measurement outcome, might not be definite for you until you observe them observing it.
That is deeply weird. It suggests reality isn't universally agreed upon at the same time. What's real for my friend isn't yet real for me.
Precisely. And it's not just a thought experiment anymore. Real experiments, variations, testing related ideas like Bell's theorem with a complex setups have produced results that seem to suggest that in certain quantum scenarios, different observers can arrive at contradictory facts about reality.
Contradictory facts, like observer A measures X and observer B measures Y, and both are valid descriptions, even though X and Y should be mutually exclusive.
Something along those lines, yes. The results challenge the assumption that there's always one single objective, universally agreed upon state of affairs. It really shakes the foundation of what we mean by objective reality.
A reality that might be fractured or observer-dependent at its core. Is there any way out of this? Any interpretation that saves objective reality?
Well, the source material we looked at mentions one possibility. Really focusing on measurement not as something mysterious involving consciousness, but as a straightforward physical interaction. It either happens or it doesn't. No half measures, no superposition of measurement itself.
Treating the measurement device itself like a quantum system, but one that decisively clicks one way or the other.
Sort of, trying to ground the collapse into a physical process. But even then, the implications of those Wigner's friend-type experiments remain deeply puzzling. The idea that objective reality might fray at the edges under quantum scrutiny is radical.
Yeah, it really is. Which leads us, I think, to the final layer here, the deepest one. If all this strangeness is happening, superposition, uncertain properties, maybe even fractured realities, what's actually going on underneath it all? And can we ever truly know this idea of a hidden part of reality?
Right. So if the wave function describes the particle, maybe the wave function is the fundamental reality for that particle. It contains all the information, all the possibilities.
Okay, so maybe that's the true picture.
But here's the catch, the really profound limitation.
Mm.
You can never fully measure the wave function directly. Never.
Why not? If it's the real description, why can't we just measure it?
Because the wave function isn't like a number you measure on a dial, like voltage or temperature. It's a complex valued object.
Complex valued, meaning it involves imaginary numbers, like the square root of -1.
Exactly. It has both a real part and an imaginary part, or you could think of it as having both an amplitude and a phase. Our measurements, however, only ever give us real valued outcomes. Probabilities, positions, energies. These are real numbers.
So it's like trying to see a 3D object using only its 2D shadow. We lose information.
That's a decent analogy. Because it's complex valued and our measurements are real valued, we can mathematically show that, at best, we can only ever extract about half the information encoded in the wave function from any single type of measurement.
Only half. Wow. Not just difficult to measure, but impossible to fully measure.
Impossible to capture all the information directly in one go. No matter how clever our experiments get, this mathematical structure seems to impose a fundamental limit.
So this isn't just us needing better detectors. It's built into the physics. A part of reality is fundamentally, inherently hidden from direct view.
That's the staggering implication, yes. A veil that we can't lift entirely, not because we aren't smart enough, but because the nature of quantum reality itself involves aspects that are inaccessible to our real valued measurements.
Okay, let's try to sum this up, because this deep dive has really taken us through some mind-bending territory. Quantum mechanics. It's not just weird particles doing weird things.
No, it goes much deeper.
First, it hits our basic expectation that things have definite properties, like location or spin, even when we're not looking. Quantum says, maybe not. Maybe things are inherently fuzzy, multiple possibilities at once until measured.
Right. That core assumption of definiteness just dissolves at the quantum level.
Second, it challenges the idea of a single shared reality. Experiments based on Wigner's friend suggest maybe, just maybe, different observers can experience different equally valid realities in certain situations. The idea of objective truth gets shaky.
Deeply shaky. The very notion of observer-independent reality is put under pressure.
And third, this final point, even if there is an underlying reality described by the wave function, we might be fundamentally limited in our ability to access it fully. Part of it remains hidden, intrinsically, due to its mathematical nature.
Yeah, about half of it, potentially forever beyond direct grasp. What really stands out to me after digging into this,
Go on.
it's this paradox, right? The mathematics of quantum mechanics is stunningly successful. It predicts experimental results with incredible accuracy. It works beautifully.
It's one of the most successful theories ever.
Exactly. And yet our human intuition, our concepts, our language, they seem fundamentally inadequate to truly grasp what the math is describing about reality itself.
And that is a powerful thought to end on. That the universe might operate on principles that, while mathematically precise, just don't map neatly onto the ways we think and talk about the world.
It makes you wonder, if our language and concepts fail us here, at the very foundation of reality, what else are we missing? What other aspects of the universe might be structured in ways that are just, beyond our current capacity to even articulate, let alone fully understand? It's like the universe keeps some secrets, not behind a locked door we can eventually open, but woven into its very fabric.